Hey guys, I'm just posting a short video here to just cover just sort of one more case. It's not necessarily totally required, but it will help you on one problem on the homework. So if you get confused about that problem, you can take a look at this. So really sort of the goal here is we're going to look at an example of a triple integral that we have to set up at least in this integration order, which I'm going to use, have to set up as a sum of two different iterated integrals. So this is an identical setup to a problem we had, except we solved it in a sort of superior integration order, dx dA, because that you can use with one integral. I just want to do this as an example because I had it prepped. But there are examples where you have to use, in any integration order, a sum of integrals. Okay, so we're going to use the dz, dx, dy integration order. Really, the thing that forces us to have two integration orders is dz. So what we want to do in this case is first take all of these sort of bounding surface equations and solve them for z. So we're going to get z equals 1/2 x minus y minus 1, z equals x minus y squared minus y, and z equals 0 as our defining equation. So what we want to do next is plot all the curves of intersection. We want to do this on the xy plane. So we have these two things we can solve for this one by just setting them equal to each other. And solving this then is going to give us the following curve: x equals 2y squared plus y minus 1. For the next curve, we have this one and z equals 0, so that's pretty easy. And here we're going to end up with x equals y plus 1. And lastly, we have z equals x minus y squared minus 1 minus y, and z equals 0. And that is going to give us the curve x equals y squared plus y. Okay. So let's just go ahead and plot these points. One thing to note, you can go ahead and sort of solve this, but Each of these have a point of intersection at the point 0, -1. As well as the point 1, 1. Right, so I see if I plug in y equals, I'm sorry, not 1, 1, but yeah, 1, 2, 1, 2. So I see if I plug in a y here, a y was 1, I get 2. Same thing up here, lastly down here. And similarly, if I plug in y equals -1, I get x equals 0. Okay, so I'll go ahead and plot these points. So I'm using just the same color as the curve. See, unlike the other case, I end up with 3 regions. So I have that region there, which I'll shade in red, and this region here, which I will shade in green. And now the thing is, what's going to end up happening here is one of our bounds for z is going to change based off of what region we are in. So if we look, say, at the region in red here, and we can figure out sort of the order of our 3 bounding equations, which remember are, so we have z equals 0, z equals x minus y squared minus y, and z equals 1/2. So on just sort of this red region here, we can look at our 3 equations. So we need to pick some point inside this red region that will evaluate these bounding equations at. So here we'll look there. So we'll look at point xy equals 0 for x and -1/2 for y. And now we look at our 3 bounding equations. So z equals 1/2 x minus y minus 1 evaluated at that point. We end up with a should be a -1/4. We have a z equals x minus y squared minus y. Evaluate that there. We get 0 minus -1/2 squared minus -1/2. So that should be a -1/4 plus 1/2. So that is a +1/4. And then, of course, we have z equals 0. So we can see that this equation is the lowest, z equals 0 is the second lowest, and z equals x minus y squared minus y is the other one. Okay, we still don't even know what one of our bounding equations is. We need to look at this other equation. So we'll look at this green region here. And let's see, one point we could pick here is x equals negative 1/2 and y equals 0. Yeah, I think that should work. Let's see, negative 3/4 should be your answer there. Z equals 0, we know what happens, and let's look at z equals x minus 0 squared minus 0, so negative 1/2. Okay, so we see in both scenarios, so here's sort of the picture we have. So we have this line here, or this plane here. I'm just sort of drawing a quick picture. And this is sort of the lowest in both of the regions. So this is always going to be our lower bound. We also have the line z equals 0. That is sort of the second lowest thing for part of it. And then we have finally this z equals x minus y squared minus y. And sort of for part of it, it's, this is not an accurate picture of all, but just to get an idea of what it looks like, x minus y squared minus y. So this is the upper bound for part of it, and z equals 0 is the upper bound for the other part of it. And so we now set up our region. So for this region, this is going to be our lower bound, and this is going to be our upper bound. But for this region, this ends up being lower than 1/2, so this is going to be our upper bound, and this is still going to remain our lower bound. So now we are ready to set up our equation. So let's do the red region first. So in this case, our x lower bound is y squared plus y. We know in both cases our y bound should be the same. They should go from negative 1 to 1. So negative 1 to 1 for our y. Our x goes from y squared plus y to y plus 1. And on this region, we have our lower bound is given by, for z is 1/2 x minus y minus 1. Whereas our upper bound is given by z equals 0. We then add to that Now this integral is going over our green region. So the lower bound for x there is going to be 2y squared plus y minus 1, and our upper bound is going to be y squared plus y. Lower bound for z will still be the same, but our upper bound here is x minus y squared minus y. Right, and I'm not going to integrate it because we already did this one. You should get the final answer is 0. And I don't think it's a particularly useful example to integrate, but this should be our setup right here. One thing to note is that, this should be just y plus 1. Oh, no, this should be, this should be y squared plus y. Okay, so yeah, one thing to note here is that the upper bound here is the lower bound here. And that ends up sort of always being the case if you ever do have to split it up into a sum of 2 iterated integrals like that. But yeah, so just sort of a useful example. I'm not necessarily going to give you anything this tough on an exam or a quiz because it is sort of a long involved problem. But there will be a couple problems like this, and also it's important to know sort of what to do in this case so you can identify when maybe you're not integrating in the correct or the easiest integration order. All right, I'll end it there.